seminar and the data science seminar, kind of colliding in an interdisciplinary mix of ideas, I hope. And the person who's going to stimulate such exciting cognitive experiences, Professor Jeremy Frey. Jeremy, I've known Jeremy for a long time. Jeremy has been like a sort of a pioneer of digital chemistry, and he's worked with ECS. He's based in the School of Chemistry, worked with ECS for what seems like forever, but he started off at Oxford and came to Southampton in 1984, and in that sense he's very much an antidote to Nigel Shadbolt. And today he's going to talk about the chemistry of data. And well, I won't spoil the punchline.
Thank you very much. So let me just turn my mobile phone now so it doesn't make a noise. Yes, I first met Des when he was a postdoc working with, or at least I don't know whether you thought you were working with Tony Hay. Tony Hay, I think, thought you were working with him. And we had I had this problem that I posed to Tony that we kept losing track of our data. And what would happen if somebody in the future phoned me up, or I think because email was, this is so long ago, people didn't even really email very much then. Phoned me up and said, you know that paper you did, that work you published 20 years ago, have you ever thought of looking at it in this way and redoing something with the data? And where would the data be? How could you transparently get from the paper to the data? And the solution, of course, was some sort of hypertext, some type of tracking system. Strangely, we're still looking for the solution to that. The problems were not just technical, all sorts of things, and I'll refer to some of that today. So what I want to do is to look at some of the aspects of where chemistry and data collide, both looking at chemical data and what we're doing with it and how we're modelling it, and indeed what chemistry can add to the general perspective of data and data sciences. And I'll try and mix it up and talk about some of the work that we've done in the context of the digital economy as e-science, and indeed some of this is influenced by a project that I'm working with in Horizon 2020, maybe one of the last that we get to work with, on defining what a data scientist might actually be, given that if we're actually using this term all the time, it might be a good idea to have at least some idea what that profession might be. I've got far too much I'm trying to pack into this talk, and yet nowhere near enough, so we'll see what we can make. So if you look me up, some of you may have done, and Les was looking me up, you found the right web page, got some of the details. But you can look me up by a number of ways, because these days you're not really known, it's your social media profile that is known. I noticed it absent from some of the social media, given though the way we work, and it's either I'm talking to researchers or undergraduates, neither of whom seem to use Facebook, which is good because I'm not on it. They only use Twitter, and I've discovered with our undergraduates, they only use things that I largely don't know anything about, which is probably safe given the recent edicts about social media that came down from the university. But if you look up on LinkedIn and various other places, and you would get, but we're not allowed to have any friends as undergraduates.
Right. We're not allowed to have any undergraduate friends.
Yeah, well, that's so therein lies the chemistry of data and the data of chemistry. Which way around is it? And that, of course, is a language-dependent issue about whether the qualifier follows or precedes the noun as well, which is another whole issue about the transnational global nature of research. Probably has ever been, but very much more obvious now, the way research is done. And of course, one of the problems with all these things is you look 6 months later, it's not just the data has changed, the format, which means the difficulty of getting any information in any automated sense of some of these websites is really quite problematic. Many of them are learning this, and if they want you to use their data, and that's a big question, they're making it available in other ways that are computationally machine readable in a much more tractable manner, and that's something that Les has worked on for many years. But I am some sort of hybrid of a physical and digital scientist. All those are QR codes which lead back to my social media profile on the lack of it. Some of my colleagues consider that I'm way over in the dark side, and they think that they wouldn't even recognise that I'm in the chemistry department anymore. But that is my core science. So a lot of the stuff that I'm going to talk about this morning this afternoon, virtually this afternoon, is informed by the fact that I'm a physical chemist and I still do, or have students who do experiments with lasers. Fortunately, I have colleagues in physics who are, and the ORC who keep the lasers running, as well as those in chemistry. But the eScience nature, so we got involved in the eScience program from about 2003 or so when it started, and we had one of the early projects, a demonstrator project, which actually turned out to be rather unusual in that it involved people. It actually involved humans talking to computers, in this case in labs and trying to do lab notebooks, which most of the other projects were far more about the middleware. At that stage, that was the thing that really needed to be sorted out, but it became more and more clear that once that was sorted out, the issue of people's interaction with the computing systems was going to be very significant. And indeed, maybe we can say even more significant, the data that people create is the issue. That led on to my work with the digital economy, which was rather broader spread, and we looked after one of the networks, the IT's utility network. I discovered the person to blame for that is not here this morning, it's Graham Bell, and he apologised for not coming, but he was the person who read sent around that saying, Jerome, you must apply for this workshop that is going on. So as it was last minute, I filled in all the sections on the sheet of paper, the virtual sheet of paper, not realising one of them was, if you were prepared to lead this network, what would you do? And apparently what I wrote down there got me into a lot of trouble. Later on I heard that it was that they didn't really know what IT was, they didn't know what a utility was, they might have known what a network was, they had 4 of them, so they thought, I'll make something of it, and they gave it to me to do. And we had a lot of fun with it, and I'll say something more about that. And then I mentioned this EDISON project, which is defining some of the aspects for the user support action for the EU on data science, and we've been working with other data science things that have actually been done for this trial. And then subsequently we've set up a small network and a little bit of money to do what I call physical and digital sciences south, and I'll tell you something about some of the things that happened there. So my vision is a split vision, these sunglasses effect, that what we're doing is science, and that's what I'm investigating. So that's my driving force. The reason for doing all the computing and the digital work and so on is not for its own sake, or not just because of the technology. It's to achieve an aim, which is to enable us to do science we couldn't otherwise do, or do science far more effectively, and use the intellectual capital of people rather than just their pair of hands doing something. Can we actually achieve far more, and certainly know a lot more about what other people are doing and use their results. The way we do that is the digital technoscape. So things have changed hugely over the last few years, and we have much better digital infrastructure for research. On the other hand, I always point out that I can buy a ticket, and not just an airline ticket, which was Nigel Shadwell's example for almost everything. But I can buy tickets, I can buy anything, Amazon it appears, in a way that if I could do that in the lab, that would be great. But actually, we don't order test tubes anymore, but that is about one of the few things we can order easily with the university's system. But actually, research is still very much, a lot of research is still very much in the dark age, and digital technology has barely touched the surface of it. I was in Denmark last year, and we were going to a Viking village, which was a great fun and a great achievement of marketing, in that it's really good to do, but actually all the exhibits, other than a few permanent ones, are all by people who are playing at being Vikings and come there to have their holiday playing at being Vikings. And we go and watch them, and it's great, and everybody has a great time. But these are the 3 norms, the 3 fates, and apparently the number of past, present, and future, and the number of knots in the road tells you how much trouble you've had having and going to have. Well, I'm not sure that choosing to do this combined sort of digital and chemical stuff was the most sensible thing to do for an easy life, but it certainly led to a lot of entertainment. So one aspect that I picked up on, because of being associated with David Raw in the past, is the whole social machine. So I could have retitled the talk, and I sometimes do, as Chemistry as a Social Machine from a data perspective, because it is critical here that we're dealing with the equipment, the chemistry itself, the people and ideas and data. And perhaps resonating with that perspective, this is the timeline, if anybody wants a booklet, I can send them one, of our write-up of our utility network. And you probably can't see all of it, but we've had libraries, human-computer issues, human data interactions, design, all sorts of different things, as well as the sort of the cloud and data perspective you might expect, threats to openness, the issue of dealing with government documents. That the government actually on the whole, well, foreign office certainly would like to release them, but realises that there's a bit of a problem here. And the biggest problem is there aren't enough former ambassadors to read the documents to check that they can release them. So what are we going to do about that? Otherwise things will just be closed. And it's a 20-year rule now, and that means there are a lot of bits of documents that can't be released because the people are still around. When it was 50 years, 100 years, it was a bit easy. So it's people, data, machines. That's something we've tried to deal with the EDISON, and the EDISON data science framework is available online to look at. I have to have the draw 4 quadrant diagram. I'm working on a 3-dimensional version of this, with another stuff, just to be able to be one dimension better than Dave. But again, it really is, it's the number of computers that are available, and computers are all over chemistry labs now. They're inside all the equipment. They're explicitly controlling a lot of equipment, still look like a computer, but as many of you will be aware, the computers don't look like computers half the time. There's a chip inside something. The number of times, and I'll refer to this later, that you think you're measuring something, but actually what you get out of your equipment is not what is actually being measured. There's a huge transformation of modelling going on. And big debates going on in the chemistry community about, no, we don't like this software. You see, why? Because the baseline is 0. Absolutely 0. And everybody knows that's not true. There is always noise, and if you can't see the noise, then you don't really know what the quality of your results are. But that's not a good marketing thing. Marketers think that having a nice 0 baseline, they've got extracted the information out. So there are lots of problems here. But computers all over the place, as well as the big systems for modelling, simulation, and so on. But what we also need is lots more people. So we've got lots of data, we can probably crunch a lot of it, but in the end what we need is lots of intelligent people to think about what's going on. An argument we make for being involved in the Global Challenge Research Funds, because there are a lot of people who might not have a chemistry lab, although the concept of a pop-up chemistry lab is something that we're working on. They may not have the infrastructure to do that, but they might well have a sufficiently good network connection and a PC or some sort of laptop, tablet, to be able to connect it and help analyse data that otherwise would be worthless because nobody's thought about it. But what is it? What chemist perspective can I give you on what's going on here? Well, of course, we have a periodic table. Hit the news earlier, not so long ago, because we just filled in the last part here. We're not stopping. There's work already going on to try and start down here. There's this purported island of stability, which is some indication it's likely to be true. So we're trying to get the next row. Lots more adventurous technologies need to do that, but chemists and physicists are working on this, and they've been working for a long time. They want to try some more. So we have a periodic table, and the point about the periodic table is it gives a foundation for building up some ideas of chemistry. In a sense, there are 2 streams here. There's the whole bit of the periodic table allowing to build up lots of compounds and understanding how atomic structure relates to molecular structure and building up a pattern. It's looking for these patterns. That's what Mendeleev managed to do. There's another side which just really focuses on carbon itself, because the remarkable thing about carbon up here is that it itself generates almost more compounds made out of carbon, hydrogen, oxygen, nitrogen, and relatively few others than all of the other compounds that we know about. And that's where biology comes in. So as we verge into biological systems, which at least all the ones we know about are all based largely around the carbon framework. So we are used to this concept of building up units. And so we have a very much initially a reductionist approach in chemistry, that we look at the molecules and we think about how they're structured, how they're built up, and how the properties of the molecule related to the properties of the atoms or subunits that are in them. And quite a lot of additivity in that sense occurs in chemistry. Things actually get to more than the molecule, and you start building up structures, crystals, materials, and so on. It starts to get more interesting in that respect, and we start to deviate from our ability to look directly at building up directly from the molecules to the materials, and there are some sense of emergence properties, which I'll come to a bit later, and how one might reverse that. But perhaps the other side of things, as well as having all these elements, all the 90 or so elements, and lots of carbons that can go in things, we intrinsically deal with a lot of stuff. So here is the definition for the moment. It's about to change. The amount of substance. Probably those of you who didn't do any chemistry at school in the last decade or two won't know what amount of substance is. The amount of substance is the quantity that relates to the mole. and we're rather slapdash and often referring to the quantity by the same thing as its unit, something which I hope you've all learned quantity calculus wouldn't do. But in this case, the amount of stuff, the measurement is a mole, because the typical amount of something around, if I take a few litres of air, I have about 1 mole of gas molecules in there. But the point is, we're already in chemistry moving away from the concept of what it is, it becomes important, but to how much of the what it is that is there. And you can have a mole of anything. So it's defined in terms of carbon-12, that's a mole of carbon-12, but I can have a mole of all sorts of other atoms. A mole of a heavier atom will weigh more, but it's still the same number of entities, and that's what turns out to be important for chemistry. But I can have a mole of electrons. The electrochemists use that, it's called a Faraday, if you make a charge of a mole of electrons. But we can have a mole of anything, because we abstracted away this concept, and the useful one, of the amount of the substance that is there. But what I point out to you is the amount is around 6 times 10 to the 23. So we are frequently dealing with the order of 10 to the 20 entities, even in a small amount of material. So we're used to dealing with big data. We've got lots of it. And we had to find ways. We don't go around normally counting single molecules. We have lots of experiments to do that, and they're incredibly difficult because the molecule is very small, and we're used to dealing with huge numbers of them together. So when we do that, one of the earliest effective areas of between chemistry and physics, and indeed a whole lot of mathematics, is to think about statistical thermodynamics. Because we have a box there, typically, say, gas, full of 10 to the 20-something molecules, but actually for most of the time, I do not need to know about what that 10 to the 20 are doing. I can look at their average properties, and if everything is ideal enough, it all works out, and I have an ideal gas equation, PV equals nRT. This is the number of moles, it's the gas constant, pressure, volume, temperature. So I can find out most of the things I need to know about the gas without ever considering the fact that it's made up of lots of molecules. Now, if I want to look in more detail, I have to progressively unpeel that and look at some of the interactions between them. And the statistical thermodynamics, so thermodynamics is the science that only needs to know about the state variables and doesn't know about the constituents. The statistics comes from the fact that we do look at individual molecules and understand how to look at all the different possibilities and sort of average over them. It's a law of statistics, it works for very large numbers. Nonetheless, we need to work out how to associate what the properties of interaction between any two of these are, and characterize it. We can characterize that or calculate it, and how we go from that to what the macroscopic arrangements will be. But once we've got some ideas of that, we can deal with rather more average properties of the system that can be investigated, can be measured, and characterize the system. By here, there are sort of almost no free variables to deal with. As you get more and more complicated and more detailed behavior you have to unwrap, then you'll get a few extra parameters coming in. But relatively few, because you can deal with the system as a whole, not having to worry about the individual atoms. Of course, we do worry about the individual atoms under other circumstances, and we'll see some simulations where we try and simulate to map from this microscopic view to the macroscopic view of the system. In fact, there was a conference I didn't get to in the US in January. One of the first times ever there was a conference being pulled in around the statistical mechanics and thermodynamics group that meets once or twice a year in the US, on this meeting in Berkeley. And basically they brought along a whole lot of statisticians and machine learning experts and so on. And we're trying to look at the interaction between statistical mechanics and machine learning. And there's some work that was published, well, actually I'm not quite clear whether it was only published just on archive, about the unreasonable effectiveness of neural networks, relating this back to the types of approach that chemists would have with statistical mechanics and understanding why the functions are smooth enough and why reality works surprisingly well. So we do have all this data. We're used to lots of data. We can make lots of molecules. We can make lots of measurements about them. And the particular issues here, we've got high-dimensional heterogeneous data. So we don't have as much data as pouring out of CERN. Although when the free electron laser imaging system XL gets going, there'll be a lot of interesting information coming out extremely rapidly. But we've got a lot. It's complex. It's often on uncertain. It's quite significant uncertainty about the data itself. Measurements are hard. Computations are reliable to a degree. But one of the things that we are missing for this, to enable us to check some of the validity of the data, is we don't have a map. So we don't have the chemical landscape. We are often searching for chemical space. This is a big deal. We could find it, but we don't know what the dimensions of chemical space are. We don't know how to relate one molecule to another in a global sense. So we can do all sorts of similarities of one molecule to the next one, and that means, if you've got a drug, and you say you've got, so the pharmaceutical industry works on finds a lead compound, so it's something that's likely to work with not too bad side effects and not too much hallucination. And then they spend some time looking for something related to that that minimizes all the problems and maximizes the effect. So finding related molecules that are really quite similar, that's hard enough. But if you say, well, I've got this drug and it has some issues in it, and I really want to treat something, but I need to find something that is similar in action, but different in all other ways, because maybe the compound you've got is gobbled up by the body, it doesn't work, or it has very difficult side effects, or it doesn't sufficiently distinguish between one target and another. So you want to try and move to another region of chemical space where the constituents are different, but have some properties that's similar. Now, if you have a normal map, you're a geographer, you like to put, you're thinking, where should I plan to put my city? Well, I'm going to put it in I want to put it in a valley, but I don't want to put it on a floodplain or something like that. You can go and look around places and find somewhere completely different that satisfies these things. We have a problem in chemistry at the moment, we really don't have that map. So there is a significant search going on by some of us to try and understand what chemical space would be. And there are all sorts of attempts being made, a number of groups. This is resurfacing, partly because we have more compounds being made, we have more compounds being measured, so the rise some years ago of chemistry allows you to make lots of compounds very rapidly, and high throughput technology allows you to make lots of measurements on these compounds quite quickly. So getting libraries of compounds with millions of compounds in them is in principle possible. So you now have a lot more data, so in principle we hope we can actually search a greater range of this chemical space and try and connect it up. And these are people making various predictions. These are low-dimensional projections for high-dimensional space, and grouping peptides or sugar molecules, graphene molecules in different regions of color.
Is this actually from real data?
Yes, that's from real data. So that's somebody, this is Raymond, he's between the US and Switzerland, and he's got, this is real data that's been taken. So you've taken several million compounds that are around and looked at some of their properties and attempted to cluster them. There are issues here. They're only working with compounds up to a limited size. They've also attempted to enumerate all compounds of a certain type up to a size. But other people have discovered that even when they try to do that fairly systematically, there are flaws. That there are compounds that we already know about that are not in those enumeration schemes. Because, for example, if you didn't know that it was possible to make a loop, make a benzene rings type molecule, and that had a particular property, it would be very easy to think you'd enumerated all of them, but missed out a whole class of molecules. That still means also we're stuck with ones that have been made. Now, at least we can extend that by thinking about other ones that could be made and doing a calculation to see if there's any chance they could be made. But that's our problem. We really want to ask questions that are really hard. We want to map out the space and then ask where the gaps are and see whether that could help us. That's an even more difficult problem because you are limited by the data, unless you can come up with some other theoretical stuff. Nonetheless, this challenge, despite all these problems of trying to understand that, big data is driving things forward. And in particular, in the materials area, there's a lot of information, and it was a little bit postage stamp collecting. You make lots of things. If you make materials out of 5 different constituents, and the slight change in the proportions of the different materials changes the properties, you've got a lot of scanning to do. And there's a lot of information, and there have been problems about reusing that information. And one of the problems is people don't report things that don't work. Right, so that's a difficulty. Some of you, as supervisors, will know that students will go on and do a load of work and not tell you until they've got the answer they think is right, which is completely the wrong strategy, which we'll come back to later. But this is also true in the literature as a whole. You can't find out all the experiments that you shouldn't be bothering to do as they were done, because nobody reports them. And of course it may well be that you could get that experiment to work, that a few years on you could work out why it didn't work and do it again, but it's really hard. So you waste a lot of time repeating things. We're getting a bit better now at scanning theses. The thesis used to have it in, but the literature didn't. So trying to recycle a lot more of this information around. Unfortunately, that usually means you've got to do a complex task of unwrapping a paper to get the data out of it. Somebody had the data, they transformed it into an unreadable object, and now you have to try and get it out again. So there are all sorts of things that we need to do there. But medicinal chemistry, computational aided drug design is very significant, similar with the with the agrotech industry trying to work there. If you think drugs are hard enough, you want the lowest concentration of the drug that you can get away with, because that's have the minimum side effects, but they tend to put it in you, right? You have a certain volume. Now think about the problem of how effective an insecticide has to be when you spray on a field. You really want it to be orders of magnitude more active than the thing that you put inside a person, because you're going to spray it on a big field and you want to make it targeted. So agrotech is an area. We are able to generate a lot of computational stuff now, big computers around, and managing all of that data and making sure that that can be shared and reused is a significant challenge. Similarly, this is just to tell you that the reaction network systems, optimization of networks, because one of the chemical space issues we've been looking at around properties of molecules, but now if you want to know how you can get from one molecule to another molecule by chemical reactions, that's a different type of connectivity. People are looking at that as well. That's a really big challenge. But let me just go back to some of the things that we do. So I mentioned here we want to be able to map out what individual molecules do and what their properties are, but in the end we're often interested in what a macroscopic amount of that material will do. And the recent, as in the last, well, I guess 50 years, but certainly increasing the availability of very high performance computing systems and the ability to deal with large amounts of data, you can take a cube of water molecules with thousands of water molecules in them, give it a reasonably well thought out procedure for calculating the forces between water molecules, and just let it go. Integrating Newton's laws. Most of the time classical mechanics will work quite well. There are a few issues, but we can take care of that. It is the stage army convention of a periodic boundary condition, so the water molecules run. If they run out this side, they appear the other side. So you have an infinite system. You need an infinite system because that's the limit that you're trying to work out. And we can work out the properties of, the bulk properties of this from the simulation. It's actually now at your level that you can simulate such sufficient accuracy because you can run them for long enough, so you average over time to give you the equivalent of averaging over lots of substates, and we can do it with large enough range of molecules that it's actually possible to, in this particular case, we're not running a cube, we're running a slab, because we want a surface of water. That's much more difficult to deal with because the surface molecules are not in the middle of the bulk, so the forces they feel are different from those of the bulk, because there's nothing above them. And we've got slabs, and we're changing the size of the slab, growing the area of the slab. And we can deal with it, keeping the number of molecules in the density of molecules in the bulk the same. And we grow this slab, and the energy changes because to create surface area requires energy. That's the surface tension. This allows the bugs to walk on water. But that is a very small proportion of the total energy of the system. And yet we can do this with sufficient accuracy that these are slightly different models running slightly different temperatures, but the slope here is telling you the amount of energy required to create some surface. And that's a mirror of doing the experiment, if you like, as opposed to the cunning ways we normally have to calculate the surface tension from here. But that just shows you the level that we can now run. These were run on machines in Southampton on the EDISON system, which is powerful, but these things can be run quite routinely now. So we generate a lot of data on a lot of particles and then ask of that system, what are the average properties that are the physically measurable properties. Here are the boxes being scaled up with the slabs. Just to point out that where we are still at the, not necessarily the forefront, but the forefront of our knowledge, the interpretation of that system is complicated because it has ripples on the surface, which are some of them are due to just randomness, some due, if you pick a system, to waves. But trying to understand what the structure of the water is, to some extent we realise now requires you to undo that ripple that is more a numerical effect than reality, and then you get better pictures. But either way, we were looking at, we then see structures of probabilities of finding atoms in a particular region close to another atom. But here's the surface tension. It's the surface tension calculated as we move our simulation along. It's a highly correlated value, so we had to deal with that when trying to estimate what the real errors were, real uncertainty. So we'd estimated uncertainty, and we were quite worried about why did it seem that the uncertainty predicted by a single simulation experiment was smaller than what we showed if we repeated the simulation experiment over and over again. And that was because we hadn't taken account the correlated effects, the correlation effect of the values here. Once we do that, we get much more consistency. However, it looks like the system is visiting some different states of the system. And one of the project students came up with plotting these sort of phase diagram plots here, recurrence plots, to have a look. And it looks like there's structure on there, but actually we realised we don't know what to do with that. It looks very nice, it's suggestive of something, and we're looking at the literature from other time series analyses areas to try and understand what we should do. So we now can create so much data now that we can look, we're not just stuck with, okay, we get the average value of the surface tension, which was what, until a few years ago, that's basically what you did, because you just couldn't simulate over long enough time to really see what was going on. Now we've got much more data, we can ask more questions. But the tools needed to do that, we're learning. And we come to talk to our colleagues in the other parts of the university. Okay, so let me just sidestep a bit. One of the things that we spend a lot of time doing is to make some molecules. My colleagues make them. I usually end up destroying them by shining light on them or doing something with them. And my colleagues made a particular compound here. Fortunately, if I'd done this different, that would rotate. It's a particular compound, and we were studying, both experimentally and by simulations, that compound sitting on the surface of water. And we used lasers to look at it. But we then got its crystal structure determined, which is one of the things we do well in Southampton. We have the National Service here. And we built a system through the eScience programs of the e-crystals to get this data out. Because it turns out that only a maximum about a quarter of the data that is recorded in the public domain about crystal structures is ever published. Partly that is sometimes because what you discover is you make the same thing as somebody else, so what will you publish? A lot of the time it's, you make something that is not what you were trying to make, but, and so there's no story to tell, so you only can publish the data, and various other things. Let alone all the stuff that's done inside the pharmaceutical industry, which they don't publish, because if they did, you'd know what they were looking at, and they don't want their competitors to know that. So we built a system to make it really easy to go from the experiments to putting the data out there. With just the basically, crystallography has a good history of being well in advance of most other disciplines about characterizing their data. So they have sort of numbers and things that tell you how good the data is. So you need still be to experience to look at it, but at least there are some indicators of data quality in there. And we can make this available, but what we made available was the provenance chain back to the almost raw data. Why I say that, the actual images that come off of the diffractometers are currently not made available because of size and some issues about software to read them, but almost back to there. If you need to go back that far, you probably just repeat the experiment. It would be the likelihood. We made those available, and get the pictures. But I put this up not only to illustrate that and to illustrate the list here of the provenance chain, but you see, chemists like looking at pictures. They like looking at graphs. Molecular graphs, physical actual plots and things. So here's an expansion here with up in the corner here, come over very well. Basically, rather than just having a list of all of these files, sitting here is computed from them backwards actually, because this was put on retrofitted, is what is the connection between those files. And it's plotted up as a graph, so if you want just to look at the final data or a bit more, you can click on one of these, there's a circle there, and it gives you that data. But if you want to know where it came from, you can follow that through the graph and go back and look at the raw data. So this is our mantra. We don't always follow as much as we should, but try and make that sequence of data available as a start. So you certainly make the numbers that are in your paper available. How many of you, well maybe you don't anymore because it's possible to use a bit for the PDFs, but I have in my career, more often than I would like to, taken a piece of paper, Xerox from the journal, gone to the Xerox machine and blown it up to A3 and measured it up to get the data off the graph. Now that's ridiculous, but now we can make all those data files available, but making them available in context and linked together and with a pathway, which is only probably what you're describing in the paper anyway, so it's more convenient, is really visually appealing, and it tells you something much more effectively and quickly about it than the list would do. So graphs are key. There's an expansion, I should remember. That's an expansion of the sort of system that's in there. This is running routinely in the National Crystallography Service. And here's one of the sorts of graphs that molecular graphs telling you what's linked to what, and in the crystal these sizes tell you something about the uncertainty of the positions. So graphs are good. Actually, just keeping in line with crystallography, I talked about the idea that we look at molecules and we design them and then we see what they build together. There is a little bit of work going on now in a number of groups in the US, in Cambridge, that they kidnapped a really good name of digital alchemy. digital alchemists. But so normally the process is you would just define a little block like this. We would get its molecular structure out. We would make some crystals, see what they would do, and then play with them for a while and see if we can get them to crystallize into different patterns. You know, quasi-crystals, whatever, layer compounds. The digital alchemy, which is slightly more difficult, is to say, I want something like this. I would like something like this because I've got one material like that, but I want to change the atom for some reason, make it more inert or something like that. Can I undo that to get back to some interesting shapes, which I would then design? And that's proved much more difficult to go that way. But understanding, now our understanding of how this, what gives rise to packing, is one of the big things that chemistry has managed to, or chemistry and physics, understanding the effects of energy, and in particular, I should stress, entropy. The issues about order and randomness and that things are frequently a stronger driving force as the energetics. Then if any of you have got, if you've got small kids, you might have ordered these packs of things that are cool packs, because unfortunately kids and adults are often pouring boiling water on themselves and doing things. And if you get one of these packs, you click it in the middle and it breaks a small sachet in there and the whole thing gets cold. And basically it's full of probably ammonium nitrate, it's not clear exactly what's in them, and a small amount of water. And it is very soluble, but when it dissolves up, it so much wants to dissolve up because the entropy is so much higher if the crystal is dissolved in the water that it will suck in energy to take it. Most reactions occur in a direction that gives out energy. The exothermic route. But these ones are so driven by the entropy that this will actually take in energy. And actually a lot of the stuff when you're trying to make nice ordered lattices is all about what is happening to the order. And some of the modelling I'll talk about later, I think we're still failing to take that into account, and we're obsessed with looking at the energetics of things when actually it's how they're packed is probably more important. So this whole thing about those arrangements, the structure of molecules and so on leads me to talk about something that we're doing with Naranjan and we're doing with Yeshe Brodsky about topology. So there's a tradition that goes back, I would argue back actually a couple of hundred years in chemistry, which is this thought that there are atoms in molecules and bits of molecules in other molecules. So that you can divide up the properties of molecules into units. You can't do it always. If you take a chain of carbon atoms, they have certain properties, and you get them longer and longer and longer, they get like waxes and so on. If you loop it up and do something different and you make a benzene molecule, that's a radically different unit, and it has very different properties, it smells different and so on. But within that, once you identify those features, a molecule that has an acidic group in it has an acidic group in it, and it will behave like that. So there's a long tradition about looking at function and also looking at other properties. In the Victorian era, measuring refractive index and so on was very common, because you could do it easily for a liquid. And they discovered that there were relationships with the refractive index of different liquids. If you took the liquids with adding a carbon atom, CH2 group along, there was a trend. You could see this. So there was an additivity in chemistry that was very useful. And we exploit that when we got to use quantitative structure-activity relationship. The idea is that you've got a molecule that you could measure some of its properties, easy properties, and predict some bio property, for example. Will this be a good drug? Will it get into a cell? If you can do that, and so basically you measure a few molecules, but then you dream up an awful lot more, and you ask, is it worth making these compounds? Don't bother to make them if the prediction is that it's going to be toxic, or not soluble, or something like that. And in the past, people would just have to think what molecules might be useful and make them. This is hopefully, if we can build the right models, is a guide that will allow you to screen out some that are not worth making. And people have used these additivity models. Essentially, all the tricks of regression modeling are used to model any data that you've got, all the way through to neural networks and so on, to try and go from a set of properties of the molecules, of the ones that you've measured, match that up to the properties that we've measured, but importantly then use that to predict the properties of a new set. And it may be that they've already made them, so a drug company might have a library of 1 million compounds, but even to screen those as an antimalarial agent is expensive. So they want to know which are the best 1,000 of those. And then they may say, well, okay, I've got these, we don't actually think any of those are being active. If we were to make another 1,000 molecules, which one should we make? Which is the best prediction? And we did a bit of work a year or two ago with colleagues in chemistry and in Spain, and they've made a set of compounds, and when they measured them, what we found was that the curve, the data, when we plotted it up, looked something like that. Doesn't matter what this was the effectiveness, and this was a particular molecular parameter. So we looked at that and we thought, well, what do we do? Well, the simplest thing was to draw a straight line through that and say, these are outliers. But it turns out we had some underlying theory that suggested actually that, it's very interesting. Oh, we've got a few more. You can tell you at the stage of teaching tell we're in when you get down to only 2 pens in lecture. So we had some idea that a quadratic was actually there was some logic, some theory behind that. But you wouldn't wish to build your quadratic fit based on that data as it was, because it's far too leveraged by these points. And indeed, when you try and do anything to check whether or not your model was robust, of course, as soon as you leave out one of these points, it goes. So what we did was, we said, fine, what we need is some more points in this region here and here. And then we can do some neat statistics just to make sure that when you're doing checking on it, you always make sure you've got points in the low, medium, and high region. So we went through and we took the compounds they'd made, because they were experts in making versions of that molecule, and we dressed them up with extra bits, went through our process predicting the value on this axis, and then said, here are 50 molecules that we think would contribute to these regions as opposed to the middle. See which ones you might want to make. And they came back and said, okay, there are 6 or 7 or whatever of them that they could easily make, and they made them, and indeed we got points in those regions, and so we could have some trust in the models that we were making. Okay, but that's been going for a long time. As I say, any new technology that comes along, chemists will try and grab and use. So the latest is actually thinking about topology. How many of you know about topology? Do I need to say much about? Yeah. Okay. Well, London Underground map, famous example, stretch, pull, and everything. Of course, it was really convenient for one of the students who's doing this that he could go on and say Nobel Prize went for topology in 2016 for topological property materials. And what was really nice is that the introduction to this had the example of spheres, donuts, bagels, and pretzels. So we see the different knots here. So these have different characteristic topological invariants to them. And if we could discover that we could characterize in some sense our molecules or their properties in some way to discover, well, sort of loosely, you could say, if it's a toroid, then there's no point in trying to find something in the middle, because it doesn't exist, it's not there. It just doesn't have that property. So we've been looking at this with regard to both the shapes of molecules themselves. So there's quite a lot of history of using topological properties to actually take a molecule. So for example, there is benzene, and you can make bigger and bigger rings that are also so-called aromatic. And when they get big enough, you can just about deal with the strain of the system to give it a twist. And chemists have now made Mobius benzene. So the interesting thing about that is benzene has this cloud of electrons on top, and underneath, if you put a twist in it, we believe it twists it round. So it's a single surface. So it has very different properties because of the way the quantum mechanics works. So there's been a lot of investigation on that sort of thing, and we're now looking to see whether or not some properties that if you treat the molecule as a graph and start asking some questions about how close different atoms are, and this may depend on the conformation. Molecules are quite flexible and they take different conformations. So we made a bit of progress here. This is looking at solubility, which is an important parameter if you want a drug to be consumable. And mapping here, so these were some particular topological invariants being used for the axes, projecting it down into 2 dimensions, and the color coding is the solubility. Well, it turns out it does work. You can see there's an arc here, and it does separate the solubility, but it also directly maps to the size of the molecule. So all we've said is that size is important, and that in the type of topology that we're using, size is coming in. So that was a good and bad. It should do that, but we need to do more, and we're working on that. Similarly, taking a much larger set of solubility data from the literature, or rather from literature and from a publicly available source called PubChem, which is a big source run by the NIH in the States. Using another technique from IASD, you look at topological issues, and it tries to connect up similar things. I won't say more about the way it's working because we're currently thinking about what it's really doing. And as Naranjan will know here, the joke is this may be real or it may not be, because what we've discovered is there are some issues with the data. And that really just goes back to my point at the beginning that chemical data is big, broad, and troublesome and bothersome. You really have to look very carefully about how data is obtained, what's happened to it. So at one level, I'm telling you that we can abstract from the original data, and I only need to know how many entities are there, but I don't need to know what the entities are to be able to make some derivation around them. That if you like making the measurements, the units don't matter as far as the mathematics is concerned. At another level, I'm telling you, no, that's not at all possible. Context of the data is really important, whether that be the units it's in, and whether that be just merely to be able to check that it's consistent across your whole data set, or it's actually telling you something about the data that you ignore if you drop that off. But also the whole experimental context, the whole pathway that gets that data needs to be available, needs to be queried. Not always is it going to be important, but if you've got several million points and you're worrying about something, you need some structure to be able to use computationally to ask the question, which one of these points which group, subset, were created by a particular experiment, or a particular lab, or at a particular time. Those sorts of things means that whole metadata infrastructure for experiments, whether they're simulation experiments, field experiments, lab experiments, or thought experiments, all needs to be clear and available computationally. I'll take another example of some of the stuff we do that crosses over into some other areas of mathematics. So I'm going to talk about what as a broad thing called about computational.
A few minutes.
Yeah. It's at we've got till 12, haven't we? And then 12:30 for lunch. Yeah, this is just lots of pictures. So crystallography. Lots of nice things about crystallography, we get crystal structures. Let me just tell you something. When you take a crystal structure, you record a diffraction pattern. You record the intensity of the diffraction pattern. Lenses are very clever about recombining that information with the phase information in there to get an image. In X-rays, we don't have that information about we don't have a lens. We can't do it that way. We've got the intensity. Things in the world are really complex numbers, and most of the time we only record the absolute value. So here's an example of why you need it. Here is an image of two famous people. Take the Fourier transform them, which is what the diffraction pattern would be. If I were collecting an image, essentially I would be collected via these X-ray techniques, I would get that. Now I will keep the magnitudes but swap the phases over and reconstruct it. And that's what it does. I haven't yet gone around to do the calculation for the current characters involved or various others, but I think that Trump and Mrs. May might well exchange quite nicely. The result is that what you've got to do is you've got to work out, the phases are really important, but the fact that those images depend so strongly on the phase suggests that even if you haven't measured the phase, we should be able to get it back. And we can do that, and in X-ray crystallography, when you get these Bragg peaks, you have fewer peaks than you get in an image, and there are all sorts of cunning ways. And what has made the biggest difference in crystallography in the last 30 years has been computers and the algorithms that are running it, not just the ability. And it turns out that before you had to do lots of different experiments, now you can collect the data and you can phase it for small molecules very easily. But for images, this is an information issue. It's how much information is contained in your sample. And if you've got, for example, that you know that your image is in the middle of your sample surrounded by black, you make sure that you know there's nothing there. That contains a lot of additional information. You're essentially oversampling, and essentially it all goes back to Shannon. You can basically do it. It's all behind compressed sensing, so on. This has been approached by the engineers, the statisticians, and the pure mathematicians to work out what's going on. But as far as imaging, this guy proposed that this could be done, and 47 years later he was on one of the early papers that actually did it. Because what you need, if you're trying to do these experiments, to be fair on it, if you're trying to determine the phase by a computational process, you must come in with something that has a well-defined phase. So you need this coherency that lasers give you, but we didn't have for X-rays. We now do. We can now do this experiment really nicely. But basically, I'll skip through that. The best thing to do is to set up overlapping images of your sample, because where you expose it with a beam here and you overlap the next beam, the bit where they overlap, the sample's the same. So there's a huge constraint there. And you just go around doing this constraint, it's called tachography. And the result is that only when you get the phases right does the overlapping region come up nicely. So this is one approach, and you can do all sorts of things. It's determining the image and the illumination at the same time. And basically we have this running now over in chemistry, and here's images of 50 nanometer spatial resolution of neurons, rat neurons grown by our biology colleagues. To do this, currently we use an iterative process going around refining it, and it may run for 100,000 iterations. But it's all Fourier transforms, almost all of it. So as long as you've got a GPU card in your PC, we can do the reconstruction as fast as you can do the experiment. Of course, you then tweak it, because if you're a biologist, you sit there with a microscope and you adjust it to get what you want to see, bits you want to see. That adjustment part is now in the computer code, and so you have to be careful. So one of our big issues, we can do all of this, and we started from sets of random phases to see, but how do we combine multiple sets of samples? How do we assess the uncertainty of all of these things and know that the reliability of them is something that we're much less clear about? I missed that bit. So let me just finish off here by going back to thinking about the labs themselves. Because all of the data that we deal with, intrinsically in the end, the reliability of it goes back to what is recorded and how much can you trust. And I'm not talking about people doing deliberately the wrong thing. There are a few people do that. It's you do the experiment the best you can at the time, and then later on you discover, the whole purpose of doing it is to find out something. You discover, I could do a better experiment. But we're not very good at passing on that information. That's what it is. And basically we want the data in context. We're trying to give a narrative. And what we're trying, my colleagues, to do in our physics experiments, for example, is to try and get people to write down the story of what they're really doing. This situationalization, as I've discovered, is called of science. You may write it up ultimately as this idealized, reproducible experiment, but people do what they do, and if we're teaching them, we need to know what they're doing, and they need to talk to us. And getting this narrative sorted out is really a problem. And the narratives can be strange. Here's some publication. Surface of the water is acidic, surface of the water is negatively charged, and it's basic. Now, what are you going to do when confronted with literature that has these contradictory elements? The answer is, this is a good topic to research, right? But cognitive computing engines do have some problems with that. I'll skip through this. What it means is that we really have to take good notes, and some issues about why you need to take notes for your own good as well as for somebody else goes back at least as far as Robert Hooke, who makes these comments of one's fallibility of memory. You should take record of exactly everything that you've done. We can learn a lot from some of these people who were doing it many years ago. We generated our own software to make it easy to get, not fill in the form about I got this compound and this one I got, but the story about what people did. And many of our students are now getting quite good at filling in some of these stories. It also facilitates an open science arrangement because you can share this. It's open source software, it can be shared around. And I would say this is Matt Todd, worked from Sydney, led from Sydney, looking at antimalarial drugs. And it's kind of a citizen science effort in that it involves undergraduates and labs around the world. Unfortunately, it doesn't involve real citizens and doesn't involve many citizens in Africa. But we're working on with other people trying to get that out, because lots of these experiments and stuff could be done in fairly minimal facilities. They were really good at taking pictures, so you really get to see what's going on. We record another whole source of data in our labs to try and understand what's doing. This is the temperature in the laser lab of all the equipment in the lab and everything. It turns out to be critical for us. So we have this data, we can recall it, we can look at it, so we can find out why things may or may not have worked as well as we want, or when they were working best. And we make sure, of course, you don't delete anything that you did in the past. Communication channels, as well as this blog type system, we're increasingly using Slack to send information back. So connecting up all our data in context is important, and we have a lot of trouble when we're trying to bring in data from elsewhere because it's in different formats and the standard electricity solution. So one solution was, let's try and rationalize the plugs and the sockets. The other was to build a plug that goes into any socket, or a socket that will take any plug. And so really clever people managed to do that. And we have quite a lot of software that will convert from one format to another. Problem is that there was, in these cases, there's a certain amount, electricity is electricity and it works okay. Whereas when we have data, there's often losses when you convert from one format to another because information is just not present in one format. So we have lots of trouble. So we have issues with reproducibility. And I wanted to show Keris's pictures here. But what I will point out here is that not just do we need data in context, but the models we need in context. And that's why we're increasingly working towards more workflow systems to be able to readily articulate and capture what it is we did with the data and what model we used, and enable transferability of that model as well as the data itself. We've been working on doing some nice things, looking at the storytelling in a wider context, but also we had some meetings on talking to your lab. So any of you know about Amazon Alexa, Well, then you can say to it, play Radio 4, and it will. Well, R1, we can also say, Alexa, ask X-ray lab, what's the temperature of the laser? And it will tell you what's the power of the laser. So we're actually enabling a lot more voice communication, and we could do it because of the data structures that were already in there. We may need to improve them, but the data is being collected, the context of the data, the metadata is there, so we can work quite nicely with it. However, what I have discovered is you can build all of this, and we work hard at getting one group of students to use it all, and the next group of students, if you don't watch them, goes back to traditional behaviour. Even worse amongst one's colleagues. And this term in-groove behaviour has been captured by the educationists, and I think it really is an issue. You have to work out how to get this into the system, not something thou shalt do it. It has to be intrinsically part of the way you do stuff. One of the problems that we have is, do any of you recognise this? It's not far away, about 50 miles away. Yes. The staircase in the chemistry department in Reading University, built by Guggenheim, big statistical mechanics person. It's a double spiral staircase. There are 4, I think, now in the world. One is in the Vatican, one is in Chambord, the Chateau, and one, I think they've now got a recent one in the US. And the reason it was done is double spiral staircases, they're 2 disconnected spirals. So the students can be coming out of the lecture theatre and down and up to the lecture theatre without crossing. It's very efficient. Don't know why we don't do it. More expensive to build, no doubt. It works really nicely. And if you think of DNA, you've got these 2 independent pathways in there. There's enough room inside a spiral to build another spiral. But the reason I illustrate it is we can have the data users and the data providers can pass in the night without ever talking to each other. And complete lack of communication. And I think that sums up some of the situations that we're frequently in. And what that leads to is, I've retaken the food thing of farm to garbage, how much of your data from your research group goes to waste. And unfortunately, I think we probably all have to admit that rather a large amount does. And sometimes for avoidable reasons. So thanks to all my members of my research group going back over many years, and all my colleagues across all the departments and universities. Without them, none of this would be possible. And thank you very much for listening. I'm sorry,
Thank you. That's a lot to digest. And ending with a free lunch.
There's no such thing as a free lunch.
So, any questions for Jeremy here on the chemistry of data?
I was intrigued to see the page that you have like the crystals, and there's a link that show the relationship between the files, provides a sense of the trace of the provenance of how one file was generated from another. Is there any sort of like common practice in the chemistry circle how to expose that information?
Not so much on how to expose it, but the crystallography community knows there are certain ways they do things using certain suites of software. There are choices, but they are fairly uniform in that way, so things are understood. So not necessarily ways to expose that, but shorthand names for some of the files and so on. There is a consistency dictionary, if you like, that will work, that allows you to piece some of this together.
So there's a convention that only experts in this field can...
It's a transparent transparent set of standards, and is encoded. It's written down in places. So they have suites of software that will check some things. But at the moment, yes, it would be a moderate expert is needed to know it. But what it means is that you can write a system to take the files and work out what must be connected, and then present it more readily.
There is also some of the work that you presented seem to have like a complex workflow and processing lots of data, and then there's an intermediary step. So I don't know whether the same practice that you have in the eCrystal website have it been done anywhere else?
There are some other repositories that expose some of this information, but not quite like we do, and not quite in that graphical way. But the crystallography community talk about this quite a lot. And there are a number of places do things slightly differently, but they all have a moderately standard pattern to do it, and there will be variations in it. But we certainly are looking at the way in which one would encode that practice, because you do sometimes get a situation, you've got 2 files about a molecule, and it's telling you something about it, and they're subtly different. And the question is why they're subtly different. And if you could interrogate the pathway going back up, you can see where, this one used that program to do this, and this used that one. And that's really then useful to track down. There's not that either is wrong, it makes slightly different assumptions. But being able to do that and do that comparison in an automated way would really help.
So you said there, the question that which of the 1,000 molecules should I test for the behavior response, drug response. The other one you mentioned is that which 1,000 do I synthesize that I do not currently have? Is there any example of doing that based on current data and their benefits?
Well, I mean,
That's what's most relevant to what we were talking about yesterday.
well, yes, although, the cost of synthesizing something versus the cost of getting out of a library and purifying whatever, doing tests, they're not necessarily so different. But yeah, well, our example was we sent to this other research group and said, look, here's a suggestion of a set of molecules to make. Now you have to think about which ones are being made. So typically, I think this is like, it is in theory happening a significant number of times in the pharmaceutical industry. That they're looking at what variations might they do. Now, sometimes this is being data-driven by the models. Most frequently, it's driven by data plus an expert thinking about it. What the next step that can be done is you can take a set of molecules, and there are programs that will take them apart and suggest routes that you can make them. And those programs, again, have variable degrees of accuracy and reliability to them. But yes, those are probably, as we have our own example, I could probably go to my colleague Richard Whitby and say, can we get some examples? The problem is it's probably being done quite a lot, and people will tell you they're doing it. They may not tell you what the molecules were that they made because of whatever reason. So.
But it's going from the descriptors to the molecule itself. Is there a unique solution?
No.
No.
Many of these things will have very similar descriptors or similar, and that again gets our problem in chemical space. So when we know that there's a region, that was our simple example here of just a one-dimensional we worry about. It's a log P, it's called. It's the light would dissolve between water and oil. So when we've done that, we then basically had to say, well, okay, it was constrained by the fact that this group makes this core type of molecules. So all we could do is stick bits on it. But we had to think as chemists which bit we would stick on it. Now there are probably some programs that would do that with some sense. And then basically you're just generating these molecules, run an algorithm that gives you, which is itself a result of having done this type of analysis in the past on calculating this particular descriptor and getting a model for that that is believed to work quite well, and getting a set of numbers and then saying, okay, these are the ones we want. So there was a certain amount of randomness going there. You can't, it's not an inversion problem. It's, these are the sort of description, this is the type of molecule I want to make. How many of these ones have some descriptors in the region that I'm interested in? Which again, makes it hard for us to break out to a completely new molecule.
Anything else? Anyone else? Right, we're about 12:05. I'll also close it there. If you have any questions, Jeremy, please come and see him over the sandwiches. And thank you very much, Jeremy.
Thank you for the opportunity.